Hello and welcome to today's class. For this class, we'll consider the study of quantum numbers. So we'll look at the concept behind quantum number. Usually, for this class here, we'll look at two distinct important concepts under quantum numbers. So we'll look at how to find the quantum number of some element, and also we'll look at how to write the SPDF configuration of an element into another element. So look at that concept one after the other. So let's start with definition of quantum numbers. So what is quantum numbers? By definition, quantum numbers are a set of four numbers that describe the energy, shape, and origination of an electron orbital in an atom. So that's a definition for quantum number, right? It's a set of four numbers. What are those four numbers? The four numbers are said to be the principal, the azimuthal, the magnetic, and the spin. Those are like the four distinct set of numbers that describe the energy, shape, and origination of an electron orbital in an atom. All right, I understand the definition behind quantum numbers. Let's look at the four types of quantum numbers. Let's look at the four types of quantum numbers. Let's look at the types of quantum number. Number one, there we have the principal quantum number, abbreviated by n. So the first type of quantum number we have there is called the principal, or perhaps principal quantum number. So it's represented by n. So n is used to represent the concepts behind. So let's start with the first type of quantum number. They're called the principal quantum number. Aside this, the second type of quantum number that we have is called the azimuthal quantum number. This man is represented by L. So we have the type of quantum number. Number one, we have the principal quantum number, abbreviated with n. Second, we have the azimuthal quantum number, that's your L. The third one, there we have the magnetic quantum number, that's your M. Some author use ML to represent it, while some use M. So let's use M in this case here. So magnetic is represented by M. So we said there are four quantum number. Number one is called the principal, azimuthal, magnetic. The fourth one is called the spin. Spin, that's your S. So some people call spin MS. So some people call this one ML, MX if you want to. So we'll use M and X here to represent magnetic and spin. All right. We said for today's class we'll look at how to write let's say I give an element. Let's say fluorine, for instance. The question will not come in this sense that write out the quantum numbers of fluorine. So look at how to do those stuff, and also how to represent an element, right? How to represent an element into another element. So let's look at these types one after the other. Now listen up. At this very point here, we need to be familiar with the concept of SPDF configuration. So now, at this point now, I need to write out the arrangement of SPDF configuration. So last class, I discussed about the concept of SPDF configuration. So we need it here. So basically, we'll be looking at, listen up. Let's say, for instance, you are given fluorine. Write out the quantum numbers of fluorine. What do you need? You need to first draw out, or perhaps write out the SPDF configuration of fluorine first. That's the first task. So now, here's another idea. What is our arrangement for SPDF configuration there? For SPDF, what's our arrangement? Go back to your initial concept. We said start with 1x, next up 2s, 2p, next up 3s, 3p, 4d, next up 4x, 4p, 4d, 4f. Next up 5x, 5p, 4d, 4f. We said after writing this pattern, what's your next task? You take what? Left hand slant this way, left hand slant this way, left hand slant this way, left hand slant this way. I have this way. Please call out our arrangement. So I'll start with what? 1x. This is 1x. When you are done with 1x, what's next? 2x. So I have 2x. What next? After 2, what's next? 2p, 3x. So I have 2p, 3x. What next? After 2p, 3x, what's next? 3p, 4x. So I have 3p, 4x. When you are done with 3p, 4x, what's next? 4d, 4p, 5x. So I have forward there, 4d, 4p, 5x. So mind you, it continue in this pattern. So it becomes my arrangement of SPDF. So we said usually we work with SPDF when it comes to the concept of quantum numbers, right? So now let's look at some example now to further explain the concept behind principal, azimuthal, magnetic, and spin. All right, example says that write the SPDF configuration of fluorine given the value of each of the quantum number. I said the example says write the SPDF configuration of fluorine given the value of each of the quantum number. So my first task there in that question said write out the SPDF configuration for fluorine. For fluorine, atomic number what there is 9. So we said draw out the SPDF configuration for fluorine first. Next, now say that the value of each of the quantum number. So I need to find the principal, azimuthal, magnetic, and spin. So let's do space. So example. The example says that the elements given there is fluorine. So I have fluorine. Fluorine, that's F. The atomic number there is given as what? 9. So we know that fluorine is F and its atomic number is what? 9. So let's write out the SPDF configuration for fluorine. For fluorine, the order I have there, that becomes start with 1x. Mind you, listen up. When we discussed this last class, we said S contain maximum 2 electrons, P that's 4 electrons, that's 6 electron, D that's 10 electron, F 14 electron. So the maximum electron that S, P, D and F can contain are 2p, S can contain 2 maximum electron, P that's 6 maximum, D 10 maximum, and F 14 maximum. All right, now with this idea, let's write out the SPDF for fluorine. For fluorine, what's your arrangement? Start with 1x. So I have my SPDF becomes 1x. We say S contain how many electrons? Just 2. This is 2. If I take away 2 from 9, left with what there? 7. So I still need 7 more. So go to the second one, that's 2x. So I have 2x. We said 2 contains still what? Maximum 2 electrons. So I have 2 here. This becomes what? 4. If I take away 9, I say I want there 5 left. I've picked 1s, 2s. What's next? 2p. So I have 2 P. We say P contain how many electron? 6 maximum. But I'm having 9 here. What do I put here? That's what they 5, right? 5, of course, 5. So mind you, P contain maximum 6 electron. But I have what? Just 9 electron here. That becomes 2 to 5. That's 9. So it becomes your SPDF configuration for what? Fluorine. All right. Second part says that find what? Each of the quantum number ranging from the what? Principal, azimuthal, magnet, and spin. Here is the task. After drawing out your SPDF configuration, we are done. What next? Listen up. Oh. To get the principal, azimuthal, magnet, and spin, what you need is what? The last orbital here. That's what the 2p to power 5. So I'm emphasizing more on 2p to power 5. That's the concept now. So listen up, listen up, listen up. In exam, some cases, they will not give you like fluorine, draw the SPDF configuration. No. Sometimes they just give you 3D to power 4 as its electron configuration. So the task now is that I don't need all this part here to get the principal. So we say the task now is that to get your principal, azimuthal, magnet, and spin, I'm just considering what? The last part, which is what? 2p to power 5. So we said we are considering what? The last part, which is what? 2p to power what? To power 5. All right, at this point now, let's try to get the what's it called? The principal, azimuthal, magnet, and spin. The easiest one to get is simply the what? The principal. Why is it the principal? So my principal is n. So n now, n is equal to 2. Look up please. To get your principal is simply the what? Number in front of what? That last orbital, right? This last one I'm considering now. The number in front of it is our principal. So n is what? N is 2. To get principal, the coefficient of the last orbital you are considering becomes your what? Becomes your principal. So since here is 2, right? So n is what? N is 2. That's your task, how to get principal. Let's look at the concept of azimuthal. So at this point now, to get azimuthal, note the following please. Right, let's look at how to get azimuthal. We said to get azimuthal, note the following. Note the following. Note that we have S, P, D, and F. At S, perhaps for S, L is equal to 0. For P, L is equal to 1. For D, L is equal to 2. For F, L is equal to 3. So note that if I have S, P, D, F, for X, automatically my azimuthal L becomes 0. If I have P, my azimuthal becomes 1. If I have D, my azimuthal becomes 2. If I have F, my azimuthal becomes 3. Now in this case now, I'm considering 2p to the power 5. This is P. Please check for P. This is P. What's azimuthal L? That's what? 1. So it means that my azimuthal is equal to what? Equal to 1. So from here now, my azimuthal is equal to 1. All right, this means that azimuthal, that's L, is equal to 1. Listen up, the task is quite simple. To get your principal, the coefficient, or perhaps the number in front of the last orbital, which is p to the power 5, the number here is 2. So my principal is 2, that's all. To get the azimuthal, note that S is equal to what? X. For X, L is equal to 0. For P, L is equal to what? 1. For D, L is 2. For F, L is 3. Now check. This is P. So for P, L is 1. So it means that my azimuthal L is what there is 1. How do you get your magnetic? Note that at this point also, note that for L equal to 0, M, which is magnetic, is equal to 0. For L equal to 1, magnetic is equal to -1, 0, and 1. Please note the following, please. For L equal to 2, note that magnetic M is equal to -2, -1, 0, 1, 2. Also, for L equal to 3, magnetic M is equal to -3, -2, -1, 0, 1, 2, 3. So note that L has maximum number 3. So L stop at 3 here. So you know I'll stop at 3 here. So here's the idea. When L is 0, your magnetic becomes what? 0. When L is 1, magnetic becomes what? -1, 0, 1. When L is 2, magnetic becomes -2, -1, 0, 1, 2. So the task is that when L is 1, you start from what? -1 to what? +1. So I have +1. All right, let me use +1. Right? Let me use +1 +2. +1 +2. This becomes plus. So right. So if I have L to be 3, it means I'll start with what? -3 to what? +3. Now let's get our magnetic here. To get magnetic, what's the task? To get magnetic now, what's the task? You said to get magnetic, what's your L? L is 1, right? So when L is 1, what's M? Magnetic is what? Is equal to what? -1, 0, and +1. But which one is the actual value of magnetic? When L is 1, magnetic has 3 value. That's -1, 0, and +1. But which one is the exact value of magnetic? Now we know that when L is 1, so since L is equal to 1, therefore magnetic is what? Is simply -1, 0, and what there? And +1. But now, how do we get the actual value? Which one exactly is value of M? Here's the task. I'll go back to my 2 to the power 5. How many electrons here? I have 5 electrons. So I'll distribute my 5 electrons under this number here. Last class, when we talked about SPDF, we draw the orbital diagram that has something of this nature, right? So look at how to distribute this here. So I have just 5 elements here. So start with what? Fill up the upper one first. This 1, 2, 3. 1, 2, 3. 3 elements. So this is 4 and 5. This becomes my last point here. So it means that this is my position 5, Abi. So this is 0 here. So it means that when L is 1, when azimuthal is 1, magnetic is equal to what? Is 0. So note that magnetic is what? Is 0. Why is it 0? We said when L is 1, magnetic is what? Is what? Has 3 number, -1, 0, and 1. But which one is the exact? To get the exact value, I'll put out this 5 electron here. I'll distribute it here. We said fill up the up one first. 1, 2, 3. When you are done, this is 4, 5. It's stop at this one, this last part here. So this last part here is 5 and attached to what? To this 0. So my M, which is magnetic, becomes 0. So I have this one here. Let's get the last one there for spin. So note that to get spin, note that when the arrow, put on place, when the arrow is facing downward, becomes -half. When the arrow is facing upward, becomes +half. So what do I mean now? To get spin now is equal to, how do you get your spin? Check your arrow from this point, from your magnetic. This last arrow here is what? Facing downward. So becomes what there? A -half. So my answer becomes -half. So my principal is 2, my azimuthal is 1, magnetic is 0 and spin is minus half. If the last, so that is that since the last electron since the last electron face downward, face down per se, it means that my spin becomes what a minus half. But if this last arrow face up, because of a plus half. So know that now how do you represent all your answers? So it means that my answer becomes what's my for fluorine now? What are the quantum number of fluorine? That becomes what? N is 2. That becomes 2, comma L is 1. That's 1, 2, comma 1. Magnetic is 0, 0, comma what there? Minus half. This becomes how to represent your answer, right? So this is how to find the quantum number of fluorine. We look at some other example using this concept right now. Let's do example 2 to further explain the idea behind the concept of quantum numbers. Let's do number 2 to explain the concept behind quantum numbers, right? All right, let's do example 2 to explain the concept behind quantum numbers. All right, for example 2 there, the one says find the quantum number of ion. No, ion is F. Find the quantum number of ion, that's Fe, right? Give that the last shell is 3d to the power 6. So my last shell is what? 3d to power what? To power 6. So this becomes your question here. So how do you solve this, man? Listen up, please. Listen up, please. For this question now, I thought to find the quantum number of this last electron. We said the task is simple. Let's get principal. Principal is n. So what's my n here? N is 3. So the number in front of the last orbital, the last shell. So this is 3. This becomes my principal. That's all. Let's get azimuthal. So get azimuthal there is quite simple. Go back here. Right? Go back here. This is a 3d to power 6. This is a d. So at d, what's L? L is 2. So when I'm having d, my azimuthal L is what there? 2. So it means that azimuthal L is equal to 2. That's the concept there. I've gotten my azimuthal, right? No problem. Let's get magnetic. When L is 2, when L is 2, what's magnetic? That's what? Minus 2 plus 1, 0 plus 1 plus 2. So when L is 2 now, magnetic is equal to minus 2 minus 1, 0 plus 1 plus 2, right? Now I'm having numbers here? 1, 2, 3, 4, 5. 5 numbers. But which one is the exact value for magnetic? We have to get that value, the exact value. What's the electron? Is a 6 electron here. So I'll distribute the 6 here. Start with what? Upper one. 1, 2, 3, 4, 5, then 6. So my 6 end at this point. Mind you, this arrow is facing downward. So that's how you get for your spin, right? But by the way, what's my magnetic here? Since the last arrow stopped at this position minus 2, so it means that my magnetic is what? Minus 2, right? We said this is 6 electron. Distribute it. 1, 2, 3, 4, 5, 6. It stopped at this point. So my magnetic is what? Is minus 2. How do you get your spin? We said to get your spin x is quite simple. The last arrow, this is 6 here, is facing up or down? Facing down because of the negative what? Negative half. So it means that my answer now becomes 3. The quantum number of this ion because of the 3, 2, minus 2, comma, minus half. So becomes your answer to that particular question. Let's look at last 2 years past question based on quantum numbers. Let's do example 3. A past question there. So it works. Let's do example 3 to see how the concept of quantum numbers work. All right. By now, you should know how to get what's it called? Principal, azimuthal, magnetic, and spin by now. So the problem says that what are the quantum numbers of an element that end with 4p to the power 5? So I have 4p to the power 5, right? So the question says what are the quantum numbers of an element that end with what? 4p to the power 5. This is a last year past question here. So you have to find the quantum numbers. So how do you do this? How do you get this done? The task is quite simple, right? We said, what's your principal from here? N is 4, right? N is 4. That whole number in front of that number in front of the last orbital, right? So this N is 4, no problem. If N is 4, please, what's my azimuthal? To get azimuthal there, this is a P. Check your P. So azimuthal L is what? 1. So my L is equal to 1. Fine, no problem. I've gotten my principal azimuthal. Let's get magnetic. For magnetic there, we said when L is 1, what's magnetic? Minus 1, 0, and what? Plus 1. So since my L is 1, if magnetic M is what? Minus 1, 0, and what? Plus 1. So this is my value for magnetic. But what's the exact value? This is minus 1, 0, and 1. But what's the exact value? To get the exact value, we said check out your for your what? For your electron. This is 5. Let's share 5 here. Let's start the up 1. Up 1, 1, 2, 3, 4, 5. This is my last one. This is 5 here. So let's get the what's my magnetic now? My magnetic M is equal to what? Equal to 0. The last arrow up, I have the last electron, and that's 0. So I have 0 as my what's it called? As my magnetic here. Let's get spin. For spin here, we said for spin, go back to your magnetic. This part here, go back to this part here. The last shell, the last electron, is the arrow facing up or down? Arrow facing downward. So when it's down, I have what there? A minus half as being my final answer for my spin. So it means that the quantum number of the last orbital, p to the power 5, becomes what there? Becomes 4, 1, 0, minus half. So it becomes your task. It becomes my answer to that particular past question. All right, it becomes your task behind how to write the quantum numbers of elements. So look at one last thing: how to write the SPDF configuration of a particular element in terms of other elements. So look at that one very shortly. How to write the SPDF configuration of an element in terms of other elements. So let's look at that shortly. All right, I said earlier that for this class, look at two things. Number one, they will look at how to write out the quantum number of given element. which we have known now. We have known how to get our spin, azimuthal, magnet and spin. So let's look at how to write the SPDF configuration of a particular element in terms of other elements. Let's start with the hydrogen, please. For hydrogen, look up, please. For hydrogen, what's my SPDF configuration there? That becomes what? 1x to power 1. This is my SPDF configuration for hydrogen. For helium, He, what's the SPDF configuration there? That becomes 1x squared. This is for helium. For my lithium, Li, what's the SPDF configuration for lithium? That becomes what there? 1s. That becomes 1s squared. 2x to power what? 1. This is my SPDF configuration for what? For lithium. For beryllium, Be, what's your SPDF configuration? That becomes 1x squared, 2x squared. That becomes my SPDF configuration for what? Beryllium. For boron, let's start with boron. That's B. That's what there? 1x squared, 2x squared, then stop, 2p to power 1. It becomes my SPDF configuration for what? For boron. All right, let's now look at something. Let's look at how to write the SPDF configuration of an element in terms of other elements. Look at helium, please. Or perhaps look at lithium, please. Look at lithium. I can write lithium as being equal to, look at lithium, Li. I can write lithium as being equal to, observe your helium. Helium is what? 1x squared. But 1s squared exists in lithium. So I'll replace this as what? Helium. So lithium can be written as what? Helium, please, in the square bracket, please. 1x squared represents what? The helium. Then I have what there? 2x to power 1. This is how to write the SPDF of an element in terms of other elements. Let's look at boron. For boron there, let's write out boron in terms of other elements. Observe that 1x squared, 2s squared exists in beryllium. So I'll replace 1s squared, 2s squared, which is this, with what? Beryllium. So I have a square bracket, beryllium this way. Beryllium is this. Now I am left with what? 2p to power 1. So it becomes how to write the SPDF configuration of an element in terms of other elements. So see you in the next class.